Hi, this is the 12.3 video. It's called arc length in space, but it also has one other thing in here. So we're going to be looking today at arc length and the unit tangent vector. So they start talking about arc length here on page 664, and they remind you that you've done this before in 10.2. So if you flip back to 10.2, here were the two formulas. This is from Cal B. This is page 573. So this is what it looked like in 2 dimensions. And now, if you notice, it's the same, but in 3 dimensions, it has an extra piece. And so, similar formula, but with one more dimension than before. And so here we have our vector valued function. So x is the function of t in the I, y is the function of t in the j, z is the function of t in the k. And so what we're doing is we're finding those 3 derivatives, squaring them, adding them together, and taking the square root. But because the derivatives, if you put them together as a vector, is the same thing as the velocity vector, and then this would be the same thing as the magnitude of the velocity vector, you can also use this formula. And this formula is basically saying integrate the speed, because remember the speed is the magnitude of the velocity vector. So they're the same formula, just whichever one is easier for you to remember. If you already remember what speed is, this one's probably a little easier to work with. So that's on page 664. And then if you turn the page to 666, you have the unit tangent vector. And so the unit tangent vector is exactly what it sounds like. It is the tangent vector turned into a unit vector. So remember from before, the tangent vector is the same thing as the velocity vector. So if you take the velocity vector and divide it by its magnitude, then you get the unit tangent vector. And notice they use capital T for that. And it's a vector, so it's bold. So here's a picture. You have a space curve, this blue space curve here. And then to find the point of tangency, you would plug in your point into your position vector, and the point of tangency would correspond to the terminal point of the position vector. And then the velocity vector is this long one. Okay, the velocity vector is the same thing as the tangent vector. But then if you make it a unit vector, then it would be in the same direction, but specifically length 1. So if it was like this, where the vector was longer than 1, then the unit vector is going to be shorter. But it would be obviously in the same direction. So that's the unit tangent vector. Okay, so here's those same 2 formulas. So here's just another way to think about it. If you take the tangent vector and make it into a vector of length 1 by dividing by its magnitude, that makes it a unit tangent vector. All right, so now let's look at some examples. This is page 667. So the first group of problems, 1 through 8, the directions are find the curve's unit tangent vector, also find the length of the indicated portion of the curve. So you're doing both things here. You're finding the unit tangent vector and the arc length. All right, so we're going to start with number 2. Sorry, I had to see my daughter was at the door. I thought I heard footsteps. I had to see who it was. So it's just my daughter. Okay, number 2, you have the position vector, this r vector, and then you have bounds on your t. That you're not going to need that until you get to the arc length. All right, so you're going to start by finding the derivative. So you take the derivative of the 3 individual component functions, and then I did the magnitude here first because if you use, hold on, let me show you. If you use this formula for arc length, and then with this formula for the unit tangent vector, see how the magnitude of the v is in both pieces? So if you start by finding the magnitude of the v, then you're ready for both pieces. So you're not plugging in any numbers here. You want the unit tangent vector just as a function of t. But here, because of the fact that I have this cosine squared plus sine squared, see how that becomes 1? So it ends up being a number, but normally it's a function of t. Here it just happened to be a number. Okay, so for the unit tangent vector, I take my velocity vector, which was the derivative, I divide it by the magnitude, and then I break it up into individual pieces, and I get this. So this is the unit tangent vector, or the velocity vector made into length 1. All right, and then for the arc length, because for the arc length you are integrating the magnitude of the velocity vector, I already found that up here, so I can reuse that. Put it here, that's what I'm integrating. Very easy integral there, so that would be arc length. Okay, next, number 10. Oh wait, check out my genius idea. Look, I taped the extra headphone jack to the wire so it won't drag across the table and drive me crazy. Isn't that a genius idea? Sometimes I amaze myself. Okay, what were we doing? Oh, number 10. I was just too busy being amazed at myself because I remembered to tape that. I forgot what we were doing. All right, find the point on the curve at a distance 13 pi units along the curve from this point in the direction opposite to the direction of increasing arc length. So lots of words here, but basically you're looking for a point on the curve. So you're looking for a order triple, and the distance needs to be 13 pi units along this curve. If you were to graph this curve from this point, so this is where you're starting, and then you're moving 13 pi units along the curve, and then your direction is in the opposite direction of increasing arc length. Okay, so we'll look at this one piece at a time. Here's all the information. So I'm going to let P be the point that I'm looking for, and that's going to be at obviously some T value. And so I have to find, first of all, I have to find the T value, and then I have to plug it in to find the point. So I'm going to start with my velocity vector, which is just the derivative. And once I find that, I'm going to do the magnitude of it and integrate it. So here is the magnitude, which is the same as that problem I did a minute ago. It ends up being 13. And then when I integrate it, notice I'm integrating at my A and B. It would be starting at 0 and going to T naught, which is this time that I'm looking for. T naught is the time I'm looking for. So once I integrate here, when I plug in, notice it ends up being 13 T naught. So the arc length is 13 T naught. So the opposite direction would be the negative of that. So negative 13 T naught would be the opposite direction of the increasing arc length. And so my distance, it told me in the problem, was 13 pi. So the distance is the same as the arc length because I'm traveling along the curve. So since I'm traveling along the curve, the distance that I travel along the curve, which is 13 pi, is the same as the length of the curve, which is the arc length, which is here. So if I solve that for T naught, I get T naught is negative pi. That's my T value. So I'm going to plug it in, and it's going to correspond to the terminal point of the R vector at that value for T. So when I plug it back in up here, so plug it back in up here for T, so you're plugging in negative pi. And so that's here, plugging in negative pi, and it gives me this point. So this is the order triple that I was looking for. Okay, so last one, 11 to 14, it says find the arc length parameter along the curve from the point where T equals 0 by evaluating the integral. Then find the length of the indicated portion of the curve. So I'll show you what they're talking about here. It's easier to show you with an example. So here's my position vector. I need to find first the velocity and then the magnitude of the velocity. So I have for my magnitude of the velocity 7. And then this comes from, hold on, here. This is where this formula is. And so it's just kind of a placeholder. It's you're going to plug in a t for it. So it's this tau value. It's just another variable, but it's a Greek letter. That's why it looks weird. But it's, again, just a placeholder so that you can plug in your t for time. Kind of like what I did on the last problem with the T naught. It's the same kind of idea. All right, so here, this is the magnitude of the velocity vector. So if it would have had a variable in it, in place of the variable, I would have put this for my variable. Okay, so then I'm going to integrate. That's my variable. Then I'm plugging in. So see, it's allowing me to plug in the t, and it gives me 7t. So that's the first part of the question. Find the arc length parameter. That would be it. And then at t equals 0, I would plug in 0 for the t. So it's the same. I kind of redid it here, but you don't really have to. Plug in 0 for the t, and it would be from, wait, hold on. Where did I, oh, there it is. I was like, where did I get that -1 from? From right here. So it would be for these values. I was looking up here at the t, but it's, these values are what I'm plugging in. Okay, so -1 to 0, go back to the 7t and plug that in, and so I end up with 7. And so here, just a note, I think this applies to a homework problem, or I wouldn't have written it here. So this is to help you with one of your homework problems. if you have to find the arc length between two ordered triples instead of between two values of t, so notice here it was between two values of t. Sometimes it may give you like 15, which I'm guessing is why I wrote these in my notes, between two ordered pairs, or sorry, ordered triples. Okay, so if you have to do that, then you would have to find the values of t that correspond to those ordered triples, and then that would give you your bounds on the t. So like for 15, what value of t corresponds to this ordered triple, and what value of t corresponds to this ordered triple, and then that would be your values that your t's are between. So for example, this is just an arbitrary vector function that I made up. If you had to find the value of t that corresponded to this point, then this is the x, this is the y, this is the z, obviously, and here this is the x, this is the y, this is the z. So you would figure out what your x, y's, and z's are from up here, and then set them equal to these points, and then you're solving. So here t could be plus or minus 2, here t could be 2, here 3 is always equal to 3, so it doesn't give me any information. So I have to find the one that works for all of these, and so it would be t equals 2. And then you would do the same thing for the next point, and that's how you figure out what your bounds for the t would be. All right, well, if you have any questions, just send me an email.